We all love pie, don't we? No, I don't mean apple pies, but a mathematician's favorite, the irrational number pi. The most beautiful equation in mathematics, as endorsed by the physicist Richard Feynman, is the Euler's identity, which involves pi. Here it is, e to the power I pi plus 1 equals 0. March 14 is celebrated as Pi Day as it is the approximation of pi to two decimal places, 3.14. There are many techniques, algorithms and series for approximating pi. Here we will look at a technique called Monte-Carlo method. This technique involves randomly throwing points within a circle inscribed in a square. Let us look at it in a bit of detail. Let me draw the square and the circle. And then this circle needs to be inscribed within a square. My drawing is not that great, but fortunately Samsung's magic will make it look better. Yeah, that's great. So this is a circle inscribed within a square. So if we look at the radius of this circle, if the radius of this circle is r, then the edge length of the square is going to be clearly 2 times r, which is the diameter of the circle. Now, out of this square and circle, we will consider this quadrant, like one quadrant we will look. So we will be focusing on this region, this quadrant. So this 1/4 of the circle and 1/4 of the square. So this is basically our region of interest. Now within this region, what we need to do is we need to randomly throw points anywhere in this region. So when you randomly throw points anywhere in this region, some points will be within this quadrant of the circle and some points will be outside the quadrant of the circle. So if you see, these points are within the quadrant of the circle, whereas these points over here are outside the quadrant of the circle. Now, in order to estimate or approximate the value of pi, what we will do is we will take this following limit. So we will take the following limit, limit n tending to infinity, where n is the number of points. N is the number of points which are randomly thrown. So limit n tending to infinity, number of points within the quadrant of circle over the number of points within this shaded square, which is the green square. This in the limit n tending to infinity will actually become area of the quadrant over area of the green square. Area of a circle is pi r squared. So area of this quadrant of a circle, which is 1/4 the circle, will be pi r squared by 4. And area of this green squared is simply r squared. So this is pi over 4. So if you find this value, number of points within the quadrant of circle, and divide it by the number of points within this green square, then you get the ratio as pi over 4. So this is known as the Monte-Carlo method. Now we will look at a simulation of this in Mathematica. So here I have my mathematical simulation. This green is the quadrant of this of the circle, and this red part is the entire square, and this red part is actually outside the quadrant of the circle. So I will randomly throw in points in this square. Some points will lie in this green region and some points will lie in the red region. And then I will take the ratio of the points lying in the green region to the total number of points, and that ratio will be pi over 4. And if you multiply that ratio by 4, we will get an approximate value for pi. So here you see I have just one point, and this point is inside this green region. So number of points inside the green region is 1, and total number of points is also 1. So 1 over 1, this ratio is 1, and this times 4 is equal to 4, which is the approximation of pi in this particular case. Now if I keep on adding more and more points, you see that I will become closer and closer to pi. See, more points are coming. These white points are inside the green region. These black points are in the red region. And once I take the ratio, I have plotted it here in this below line, in this below plot. So this blue line is the value of pi, this blue dashed line, and these pink points are basically the approximation of pi as the number of points increases. So this x-axis is number of points. I have taken 100 points, and as you can see, it kind of fluctuates randomly about pi. There is no particular sequence because here I am randomly throwing in the points, so there is some randomness, as you can see in this plot. Now because I am randomly throwing in points, this sequence of convergence to pi will be different each time I run the code. So let me show you by running the code a few times. So here this is the code in case you want to have a look at the code. So this is the code, and now you see you have a different sequence. Earlier you see the sequence, it was fluctuating below this blue line also, but now you see it is all above this blue line. So this is a different sequence. Why? Because the randomness of each point is the reason why this is becoming random. Each point is being randomly thrown in, and each time the sequence will be different. Let me run it a few more times. Yeah, it takes some time to run, and now you see, oh, this time you see it starts from below this blue line. Why? Because you see, if I look at the first point, let me show you the first point. So the first point actually lies in the red region, outside the green region. So number of points within the green region is 0. As a result, the approximation for pi is 0. But as we add more and more points, you see that we come closer and closer to pi. And in the limit n tending to infinity, that is the number of points tending to infinity, we will be very close to the value of pi. Let me run it one last time, and once again you will see there will be a different sequence. So this is another sequence. So each time you run the code, there will be a different sequence because the inherent randomness of this technique. So the next time you bake a pie, do remember the mathematician's pi.